So welcome everybody. I'm very happy to host today Dimitrios Nikopolopoulos, who currently is John W. Hancock Professor of Engineering at Virginia Tech, serving as professor in the Department of Computer Science and also in the Bradley Department of Electrical and Computer Engineering. His research focuses on high-performance computing and computer systems, and during his career, he has contributed significantly to parallel programming standards as well as to commercial system software products, including Red Hat Linux and Intel parallelizing compilers and runtime systems. He has received, among others, many awards from NSF and DOE, and published a very large number of papers in top venues and journals, and mentored a very significant number of students and postdoc. Today, he's going to present this talk on SWIFT, the system architectures and programming abstractions for resilient and efficient edge AI, which is also in part a result of the current exchange collaboration with one of the exchange grantees, Dimitrios Nikopolopoulos from the National Technical University of Athens. So thank you, Dimitrios. The floor is yours.
Okay, thank you. Thank you, Rosa, for the very kind introduction. I hope you can hear me okay. Welcome, everyone, and thank you for joining this webinar. So today I'll be talking about how we are rethinking the system stack to meet the demands of edge AI, especially now that edge AI is beginning to adopt complex models like, for example, vision language transformers. So I'm going to start with a quick look at the motivation and the emerging challenges at the edge. Things like constrained compute power, dynamic execution environments, a fragmented hardware ecosystem as well. I'll then talk a little bit about abstractions, particularly data and programming abstractions that make it easier to express and deploy AI workloads across diverse platforms at the edge. Then I'll walk through several recent systems we have developed, part of them with thanks to this Discover US collaboration. The first system is called HiPEAC. It helps scale vision language models by a hierarchical data reduction approach. I'll talk a little bit about frame feedback, which is a runtime system that offloads computation adaptively based on real-time feedback. I'll also look at techniques for virtualizing AI accelerators to enable better sharing across workloads. And this includes Parva GPU, which is a lightweight runtime that we have developed over the last 2 years. And we have developed this specifically for consolidated inference and memory reuse. I'll present a new system we're working on named Quant Pro, a very recent work, which is designed to accelerate inference from diffusion models. And I'll conclude the talk by zooming back a little bit and discuss how these ideas fit into a broader transatlantic research agenda, where we can perhaps combine strengths from Europe and the US in areas like edge hardware and AI software and co-design. And hopefully I'll leave some time for questions. So let's get started. So as I said, we are witnessing a fundamental shift in how AI operates. So in the past, in this new era of AI workloads were mostly confined to centralized cloud infrastructure, but that's changing quite fast. Today, there's a growing demand for AI inference directly on edge devices, on everything from smartphones to drones to sensors to wearable devices. And there are good reasons why this shift is happening. One is that we have a sheer number of connected devices. We have billions of connected devices globally, and each of these devices generates a significant amount of data. And instead of sending all this data to the cloud, it's becoming more efficient and perhaps more intelligent to process the data locally. So at the same time, we're witnessing a rise in applications that require instant responses. So if you think, for example, gesture recognition on augmented reality or autonomous navigation or detection of anomalies in various environments like power grids, these are systems that simply cannot afford the latency of cloud round trips. So whether it is about improving responsiveness or to enable offline operation or to scale across distributed systems, there is a growing need for edge AI. It's rapidly growing. And with that, of course, comes a range of new system challenges, including how to make large AI models fit in small systems, how to run fast, how to adapt to constrained environments. And this is exactly the type of challenges that I'll be discussing a little bit today. I'll focus on three systems that address different aspects of these challenges. Now, having said why edge computing is gaining momentum, let me talk a little bit more about the benefits that make it also very compelling, right? So when we bring computation closer to the data or directly where the data originates, we have at least three important advantages. One is privacy. So if we have sensitive data like video from a security camera or health signals from a patient, this can be processed locally. And we can eliminate cloud transmission, and we can reduce exposure risks and also any risks of regulatory compliance. Second, we have potentially latency reduction. So processing at the edge eliminates round-trip delays to distant servers. And there are many applications where even milliseconds of communication delay matter. So local processing makes a difference between functional and non-functional systems in this case. And third, energy savings, right? So all these devices, when we ask them to transmit data, they consume a lot of power. Transmission of data is power hungry. So local execution, local AI certainly can reduce the energy cost because of these transmissions. I think that these advantages combined together create edge AI systems that are particularly compelling, particularly appealing for many applications. Now, back to the challenges. So I'll focus on three fundamental challenges that you are probably all familiar with, all those of you who do research in this area. One critical challenge that we face is balancing latency and accuracy, right? Or quality of the result, whatever quality means for the specific applications, while we operate under very strict resource constraints, right? So on edge devices, we don't have data center scale compute power. So what do? Do we shrink our AI models? Do we reduce the resolution of our input? Do we drop tokens, right? So we have a whole gamut of optimization, and each of them improves speed, but potentially degrades quality. And this chart here shows just various instances of mobile net and how accuracy and latency exposes interesting trade-offs. So you're basically walking like a tightrope. So if you do too much optimization, you lose accuracy. If you do too little optimization, your response time may become very high. So there's a balancing act there that defines many of the systems problems that I'll try to talk about today. Of course, my group, and because of my own background and our students' background, focuses on dynamically managing these trade-offs, right? So having adaptive techniques to optimize the data paths of inference or control offloading or do introduce other methods to improve device capabilities in real time at runtime. The other challenge is variability, right? You probably are very familiar with the methods of offloading. So offloading is a technique where you take tasks and you send them to nearby servers, and it seems like a very obvious solution when you have device constraints, but it has its own set of complications. In practice, when you deploy offloading, you must navigate significant environmental variability. So many times when we offload to edge servers as opposed to traditional large-scale data centers, we don't have services like elasticity, for example, that we have on the cloud. You cannot simply spin up new containers on demand easily. When you have dozens or hundreds of devices that share the same edge resources, You may have queuing effects. Queue lengths can grow unpredictably, perhaps leading to missed deadlines or degraded user experience. Your networks, of course, add a lot of uncertainty. Wireless connections, which are prevalent and, of course, are mostly used in these cases between edge device and servers, they fluctuate in quality and speed because of interference, because of mobility, because of congestion, depends on the time of the day, even the weather, right? So any device like a drone or a headset might experience dramatic bandwidth changes just by moving a few meters or encountering a new obstacle. And this whole variability, this unpredictability of the environment calls for dynamic and adaptive approaches, right? And I'll talk a little bit about frame feedback, which is one approach to use control theory to improve offloading. The other challenge is all too familiar to this community, of course, is another memory wall. There are severe memory bottlenecks. There's a memory wall in Edge AI just as challenging as the memory wall that we have been fighting for decades in all kinds of computing systems. One particularly telling example is when you're working with high resolution visual inputs. You face critical memory problems. So if you use transformers or transformer-based models, like the ones that you have in modern vision language systems, then you have a dramatic increase of computational requirements and dramatic increase of memory requirements. So even a single 4K image can generate thousands of tokens, hundreds of megabytes of data, right? And each of them will require its own embedding vector and attention data. So there's an explosion in the intermediate data and the intermediate representations of these images, and this rapidly consumes available memory. So when you work with devices that don't have a lot of memory, and I'm not saying tiny devices, even devices that have maybe several gigabytes of memory, even there, things are very challenging with these models. Right? So you hit hard memory capacity constraints, and you hit them long before you reach your computational actually limits. So one of the systems that I'm going to talk about higher today is trying to fight this problem. Okay, so from challenges, let's move on to some solutions, some ideas. So I have outlined several critical constraints that we face in Edge AI. And it's clear that addressing these problems needs more than just tweaking AI models, right? So we need to just rethink of how AI workloads work at the edge and what can different levels of the system stack achieve here. And I think in this challenge, abstractions become very essential. So rather than treating AI models as just opaque black boxes, what we do in our research is we try to focus on exposing and controlling some of their internal data structures and their internal data paths, right? And by making these structures and paths programmable effectively or adjustable, if you will, right, we can tune, we can adjust how inputs are processed, which information is prioritized, and how computational resources are allocated given their limitations. So HiPEAC, which is the first system I'm going to talk about, and in some detail exemplifies this idea, this approach. What this system does is it provides a lightweight abstraction layer that allows us to do very fine-grained control of visual tokens and visual token budgets in vision language models. So that's the abstraction, the visual token budget. And instead of processing all the input tokens equally, what the system does, it tries to intelligently filter less important visual information from more important visual information before it gets to the point of being processed by the language model. All right, so let me show you a little bit how this system accomplishes this goal. And let's start a little bit with the insight of HiPEAC, which also leads us to its core, I guess, innovation or the core novelty. So when we started studying vision language models, we observed that there is something very characteristic about their attention patterns. So basically, simply said, these models don't treat all parts of an image equally. So instead, they naturally focus on certain regions of the image that contain more valuable information for understanding the overall content of the image. And of course, this is very intuitive. This is something that has been in the minds and at the heart of many previous image processing work, right? So this leads us to a good question. So can we leverage this prioritization to make inference on edge devices more efficient, right? So we analyze how attention flows through transformer models. Basically visual models, visual transformers. They are also called VITs, right? And at the heart of these architectures, there is something called a special token or a classification token. It's referred to as CLS, right? And it serves as an aggregation point. This token is prepended to the sequence of image patches and collects information from the entire input during the attention process. So we zoom on this classification token, and then we try to score, right? So we use CLS scores, and we try to see what tokens contribute most to the understanding of the image and what tokens contribute less to the understanding of the image. And what we discovered is summarized in this figure. Just to walk you through this figure, there's a distribution of attention, which is dramatically skewed, right? So you have about 20% of your visual tokens, and these receive about 60% of your total attention. And then if you go to 40% of your visual tokens, they will receive about 80% of the attention. And this is a pattern that is held consistently across many benchmarks and data sets that we tried. And this basically gave us the most important insight, which became the foundation of HiPEAC, this system. So we extract these CLS, the classification token attention maps, from both early and late transformer layers. And then we can estimate two properties for each image region. One property called the visual content density, and the second is the feature importance for the model understanding. So this is how HiPEAC is organized. It's basically a two-stage process that we try to illustrate in this diagram. So the first stage distributes a token budget. So and you can see it in the upper flow of this image. So the HiPEAC first establishes a token budget. It partitions the high resolution image into different subregions. And for each subregion, you have a clip visual transformer that analyzes the visual importance of tokens and their spatial distributions. CLIP, if you're not familiar with, it's a multi-modal vision and language model, which is based on a vision transformer. That's why it's called CLIP, VIT. So you get visual features and a causal language model to get the text features. Now, by doing this partitioning, we enable dynamic allocation of the token budget. So we try to assign more tokens to information-dense regions and fewer tokens to simpler areas. So that's the first stage of HiPEAC. The second stage, which is the bottom flow that you see in this image, in the lower flow, we use feature importance scores to identify which specific tokens within each region contribute most to the semantic understanding of the image. And only these top-ranked tokens are selected, ensuring that each subregion stays within its allocated budget and preserves the most critical information. So we have basically an adaptive token selection strategy based on this abstraction of a token budget and the importance basically of different image regions. We significantly reduce processing requirements, and of course we reduce also space requirements, which is important for platforms with limited resources. So this slide shows you a sample of the results taken from a AAAI paper that we published recently back in February. This specific slide comes from an evaluation of a Lava 7 billion model. It uses an NVIDIA Tesla GPU, a P40, which has 24 gigabytes of memory. So not necessarily the most powerful or the GPU with the most capacity. And I think that the results are quite compelling. If we just select 20% of the original visual tokens using our token classification strategy, we have almost 5-fold increase in throughput, and a 78% decrease in latency, and a small also decrease in GPU usage, probably around 14%. But if you actually do batch processing, so this is for a single basically instance, if you do batch processing of your regions, then when you exhaust the available memory of the GPU, right? So then the per instance savings go up to 30% at the batch size of 4. And you sustain the quality of service. You still have responsive and stable inference times at scale, which is critical for a real world scenario. And all these efficiency gains come without compromising quality. We compare to various state-of-the-art solutions. PRU-merge in particular was one quite prominent. And we either maintain or improve performance across various transcription tasks and Q&A tasks on images, despite processing only a small percentage of the tokens. So this confirms our core hypothesis that if we do attention-guided token selection, then we not only reduce computation, but we preserve accuracy and semantic information for the images. Okay, so we've looked at a system that addresses high-resolution visual input challenges and memory challenges, memory requirements. So next, let's look a little bit into an equally important problem, which is deciding where to process things, where to run your inference tasks, right? So if you have these edge cloud systems, then you have workloads that must be strategically distributed or offloaded between local devices and remote servers. And of course, there's a number of good static offloading strategies that assume relatively stable system conditions, but this assumption just rarely holds in practice. In real-world deployments, several things can undermine static offloading approaches. That can be network congestion, that can be variable server loads, that can be contention for resources, and so on and so forth, right? So I'm going to talk a little bit about frame feedback, which is a simple system. It's a closed-loop controller that continuously monitors runtime conditions and adjusts offloading policies in real time. And this adaptive approach tries to ensure consistent performance, even if the environment is unpredictable. Let me dig into frame feedback a little bit here. So what we do is we implement a real-time feedback control loop that dynamically regulates the distribution of the workload between the edge device and a GPU-equipped server. And we base this on a proportional derivative controller, a very, very simple controller. We have some details in the paper. It's an IPTPS paper, where we use a very simple yet effective metric, which is just deadline violation. So we expect frames from a video to be processed within a certain deadline, and we are offloading frames to a server, to a GPU server, and we check how frequently offloaded inference results from the frames arrive too late for real-time applications. So we have a real-time constraint basically there. So it's a very simple system that operates on a straightforward principle of balance. So when responses consistently meet their timing requirements, then the system gradually increases the offloading rate to maximize efficiency upon detecting latency violations, whether this is because of congestion or server load or any other effect. Then the system automatically adjusts the balance and redirects more computation to the local device to maintain responsiveness. Now, if you wonder what is interesting about this system, right? So it seems like a very simple system. Is there anything else? So the nice thing about it is that it's a model-free system. So there's no complex profiling, there's no training data sets, there's no prior knowledge of network conditions. So it just responds to real-time quality of service signals. And this makes it remarkably adaptable to changing conditions in different execution environments, right? So we went with a solution, and we received a lot of comments in the reviews about this. We went with a solution which is almost dead simple right here, because we didn't want to go through this process of, okay, let's train, it was very hard, to train systems, offloading systems based on all the potential conditions that may arise during the execution of the actual offloading tasks. And unlike good static approaches, deep decision, for example, was a good system that we were comparing against. Unlike approaches that do binary decisions, either offload or not offload, basically, our system was able to find better operating points and achieve up to 2 times higher throughput. So this is a heavy slide here. It's a very busy slide. I'll try to walk you through it. So this is how our system for feedback and various other offloading alternatives work in a scenario where you have video processing, right, between the local device and the GPU server, frame processing, and you have a spike in server load between seconds 35 and 85. The horizontal axis in this chart is seconds. So the figure compares 4 approaches, and they all track throughput over time. So P is throughput here. Always offload is obviously an approach where you initially perform, you always offload to the GPU. And this performs initially just fine, but then it fails almost catastrophically because of the server overload, right? Dropping to almost 0 throughput as the system becomes overwhelmed with queued requests. So you have these orange diamonds, if you can actually see them on the screen, and they show an approach called intervals. This is a static time-based approach that alternates between local and server processing in intervals. And it tends to be more resilient, of course, than always offload, but it still suffers from significant drop in throughput during the load spike. Then you have something called PO. PO is a very simple control mechanism that doesn't have the derivative component of our approach. So it reacts to server conditions, but experiences more dramatic fluctuations and slower recovery. And finally, frame feedback is our full controller, where it's the blue dots that you see here, the dark blue dots. And it maintains consistently better throughput during the experiment. And you can notice how gracefully that it adapts more gracefully as the server load increases, reducing the offload rate between seconds, I would guess 50 and 60, and then slowly, gradually coming up to maximize throughput again. So the period of interest here is between seconds 35 and 85, where you see the blue dots tend to be above the other dots. So you see that this continuous control loop performs quite well, despite that it doesn't use any kind of system profiling or assumptions or training a priori. Okay. So we've looked at HiPEAC, we looked at frame feedback. So we looked at when and how much to offload based on real-time system conditions. Now, there are other scenarios where offloading is just not an option. For many reasons, can be privacy requirements, lack of availability of good network resources, other limitations. So this brings us to our third system that I'm going to talk about that specifically focuses on GPU inference efficiency. So I'm going to talk about Parva GPU, which is a collaboration between us and a Korean university, actually, Cheolho Hong in Chunghan University. But it's something that we have brought in this collaboration, this European collaboration, as well as a continuation of this project. And I would like to talk about this a little bit. So this system targets specifically memory bottlenecks and throughput limitations that are prevalent on GPUs when you load AI models and you do inference on GPUs. So the idea is, or the motivation for this problem is, can we do efficient inference on GPUs and consolidate models as well, right? So can we pack the GPUs more tightly? Can we improve their utilization by consolidating models, right? And we're targeting GPUs that are limited memory GPUs, not the kind of GPUs that have 80 or 160 or the highest amount of memory, but GPUs that you probably find in small private clouds, for example. So let me talk about the system a little bit. It's a fairly complex system. It's summarized in a supercomputing paper. But basically, its breakthrough is that it makes GPU sharing very practical. And it does so by enabling some unique, first-of-their-kind fine-grained partitionings, spatial partitionings of the GPU, right? So there are technologies to partition GPUs. Of course, they have been studied a lot. You might be familiar with the multi-instance GPUs and the multi-process services of NVIDIA, of course, which provide some basic hardware-level isolation. We do take these technologies, these foundations, and we enrich them with a good software orchestration layer that does fine-grained GPU resource allocation, okay? So the architecture of part of a GPU follows a two-phase workflow. We have what we call a segment configurator, which analyzes its workload. It does runtime profiling, and it applies two algorithms. One is called what we call optimal triplet decision, which identifies the ideal combination of micro GPU instances and process count on the GPUs to maximize the throughput while meeting the SLO. Then you have a second algorithm called demand matching, which tries to compute the optimal number of segments of GPUs needed for high request rate models. And together, these two algorithms, the segment configurator and the optimal triplet decision and demand matching, they try to minimize what we call internal slack, right, in the GPU. So when you have internal partitions of the GPUs, predefined partitions of the GPUs, the slack, the idle spaces that you have there, you try to minimize with these algorithms. Then there is a third component called segment allocator, which basically does a packing algorithm to map segments across available GPUs, model segments across available GPUs, right? Notice that the basis of this is segmenting models, right? So we split up the models, right? And we try to find interesting ways to distribute segments of the models between parts of GPUs, right? Fractions of GPUs. The segment allocator tries to minimize external fragmentation. So these unusable GPU regions that typically go wasted. And the final component of this system is a reallocation component. If we do detect external fragmentation, then we try to take any large segments that have been unused and partition them into smaller segments and try to reallocate on these idle devices. I oversimplified a very long discussion and a very long paper, but what I'm trying to explain, I guess, here is that you have a really NP-hard optimization problem. You have two ways of partitioning a GPU with constraints on how many partitions you have and what is the size of this partition. You have infinite ways of splitting a model into a segment, and you have to map this segmented model to the partitions of the GPU, right? This is what we're discussing about here. But by doing this trick of separating segment configuration from allocation, then we do actually improve very much GPU utilization. And we do that with very low runtime overhead. Now, the catch here is that this is possible only for small models. So this is a work that we did originally with very simple, small size convolutional neural networks and deep neural networks. So the previous generation of AI models. So in terms of real world performance, this is testing on a cluster with A100 GPUs with 6 different scenarios of packing multiple DNN models on the same GPU and having specific SLO requirements. And the headline here is that basically our system requires 30 to 45% fewer GPU space or fewer GPUs, right, than the best alternatives out there, things like GPU-led igniter, MIG serving. So there have been prior work there that we have to compare against. So this is a quite dramatic reduction that comes from this very strenuous effort to remove any GPU underutilization and GPU slack. And we actually measured the slack in these solutions. So our internal slack is under 5% and our external slack is 0. So we have very good efficiency gains without compromising performance here in this scenario. Now, what we're working on now is, of course, and what addresses the most, I guess, a very valid criticism is that, right, nobody cares too much now about CNN models, but we do care about larger models, right? So how can we accommodate larger transformer models and address the significant memory bottlenecks of these models, right? So we're working on extending the system with better ways to manage key-value caches, actually. So together with the smart ways of partitioning the GPUs, we're looking into smart ways of managing multiple key-value caches, KV caches. For those of you who work with transformers, you know that you have the model and you have a KV cache that you try to use as much space as is left available by the model to cache things, right? To cache results as much as possible. That space varies. It depends entirely on the model size. So we use similar ideas to the ones we pursued in HiPEAC and other projects in the past, which is basically to try to manage KV caches based on the significance of the data in the caches. So we do that. We do some sort of significance-driven or importance-driven caching here, okay, that we're working on. And we're also looking into how can we actually implement those caches in heterogeneous memory systems. So not just the DRAM, but how can we potentially use any other memory that's available in the system, perhaps some remote memory, perhaps some disaggregated memory, right, to manage these caches. So what we're working on now, and I'll be happy to talk to any of you interested more offline, is how to actually support this packing and virtualization for larger transformer models. And a key component of this is this lightweight KV cache reuse across inference steps. Okay, so the final system I'm going to talk about briefly is QuantPro, and this is very early work, in fact, unpublished work yet. You probably know about diffusion models a little bit, right? So they are a fundamentally different class of inference models. So unlike classification or vision language models that we talked about earlier, these generative models require iterative computation with a very big memory footprint and expansive intermediate data. Their sequential process creates very long-lived key-value caches, and these expand dramatically over time. So it's really challenging, right, to use these models in any edge hardware context, right? Although they are of growing importance for applications like image generation, content creation. So they are these models that enable the very artistic, very high quality image generation that you may see in places like Claude or ChatGPT maybe. So this motivates our next system, which we call QuantPro, and I'll just gloss over the idea of QuantPro a little bit here in the interest of time. So at the heart of a diffusion model, you have this iterative denoising process. So, and this comes in hundreds of steps, right? You have hundreds of sequential actually steps, and in each step you refine the output of the previous step, right? So you have two critical bottlenecks here. You have long inference times and you have high memory demands. And of course, these are amplified if you're working in any device that doesn't have a lot of compute power or a lot of memory. The idea here is to progressively improve the image quality. It's simple, right? So you use diffusion models to generate remarkably high quality images or videos or other media. Now, you can apply, and people have tried, some standard optimization techniques that we have been working on and people have been working on for years on conventional image processing models. You can do, for example, quantization, right? So you can do static quantization, which is very effective in many domains. It actually fails here because the information content in each of these denoising time steps evolves a lot. You have early steps where you have a lot of stochastic noise. They are dominated by stochastic noise. and you have later steps in this refinement process that encode increasingly detailed structure because the image improves. So if you just apply a uniform quantization across all the iteration, then you have very steep quality degradation. And you just fail to capture any temporal variation in the images. If you try to do parallelization, of course, which is another very important technique and very effective technique, it doesn't fare very well either. So you could divide this workload between devices, which is a common approach, a common tactic, but you have very tightly coupled intermediate states between the iterative denoising steps. And this creates a very high communication overhead. Particularly if you attempt to do the traditional thing where you partition the image into patches, into regions, and you try to apply this data level, this data level parallels. So this overhead often eliminates any benefits of additional compute resources. So this leads us to a question, so can we co-design a quantization approach that is better for these diffusion models and a parallelization strategy that is better for these diffusion models? And can we do it in a way that respects these temporal dynamics of diffusion, which are very different than in previous models? So just to give you an idea of what we're working on here, so we have two techniques. One is called group-wise dynamic quantization, which we do per denoising step. And the second is called parallel patch processing with reuse of activations. The group-wise quantization is something that we apply for weights, and the dynamic quantization is something we apply for activations, and we tune them per time step. So this lets us preserve the fidelity across the entire denoising process. In parallel, what we do is we try to exploit patch-based parallelism across GPUs specifically. So we do split the image into segments, and we do run the denoising in parallel. And to reduce latency, communication latency, what we try to do is we try to reuse high-level activations across time steps, wherever the model architecture allows us to do so. So we try to reuse cache, if you want, these activations to save some compute time while keeping the realism of the image that we're generating intact. And we have some preliminary results on A30 and A100 nodes where we see some meaningful reductions in latency while we're retaining quality metrics like the feed score and the clip score. These are quantitative measures of the compatibility of image and caption pairs. And clip, this is feed, and clip is a measure of compatibility as well. So what we try to do is that we try to offer a scalable and hardware-friendly way to deploy diffusion models in real-world settings by continuously improving our quantization and exploiting parallelism at the same time. Okay, so I'm going to move towards finishing here, so and hopefully leave some time for questions. So I'd like to shift from technical specifics of diffusion model acceleration and the other systems that we discussed to a broader research vision, one that is inspired by a project that I am coordinating. It's a US island project. So for those of you who are not familiar with this, there has been an agreement between the National Science Foundation, the United States, and the Republic of Ireland and Northern Ireland that has been in place for many years, decades actually, for transatlantic collaboration. And it broadly covers areas like sensors and networking and energy and some other areas. And we applied for funding for this scheme, and we got a grant back in 2023. The grant is called SWEET, and it focused on edge AI, specifically for wearable technologies, but more broadly for any emerging technology there. So this project brings together many researchers from Virginia Tech, from University College Dublin in Ireland, and from Queen's University, Belfast in Northern Ireland. And we developed techniques that span the entire continuum. So we have really a project that connects the cloud and edge platforms and swarm intelligence and IoT systems very much along the lines of the US Discover effort in Europe. Within this framework specifically, we're advancing 4 strategic priorities, which I highlight in blue, I guess, in this figure. One is AI-driven resource management that adapts dynamically to workload and infrastructure constraints. We have collaborative development frameworks to streamline innovation across different institutions and geographies. We're trying to improve human AI understanding, ensuring that systems remain transparent and trustworthy. And we are also investing in cross-national partnerships, right, that can extend our scientific impact beyond the boundaries of our continents or our countries. What this slide here tries to emphasize is there is a continuous flow, basically, of data, of models, of solutions across this interconnected landscape. In the outer perimeter, you see the components of the computing continuum, and within the inner boxes, you see all the efforts that we're undertaking here to lead to an integrated system. If you want a little bit more detail, I'm happy to share. We're using RISC-V-based hardware technology developed primarily in Dublin, in Europe. We use various significance-driven computation techniques pursued in Belfast, and we're using new resource allocation strategies and algorithms that we primarily develop here at Virginia Tech, and we also do the integration of the system here at Virginia Tech. As we are exploring how to take the experience of this project and realize a broader vision, the challenge that I think is foundational, that I think I would like to stress here and becomes clear to me at least, is that traditional AI systems are built in silos, right? And this has been a problem for many complex systems. So you have runtime schedulers, hardware, memories, right? So all these components and many more actually are typically optimized in isolation. So you have a fragmented design approach that hampers coordination. And of course, this opens up the exciting opportunity of co-design. I think that collaborative EU and US efforts like Suite, like the Discover US, they have the chance to redefine this paradigm, right? So we can embrace co-design methodologies. We can integrate these components into functional systems. We can apply them against realistic workloads and realistic applications. So there is an opportunity, thanks to these collaborations, to shift from siloed system-level design to co-design that leverages the strengths and the best that we have to offer from our research organizations in both sides of the Atlantic. Now, the other thing that I wanted to stress is that all these problems that I talked about today, I talked about, I don't know, memory fragmentation, hardware fragmentation, very technical terms, right? So all these are persistent barriers to good AI, to scalable AI. They are barriers for scientific applications. They are barriers for autonomous systems, for cyber-physical systems. So at the end of the day, these problems stand in the middle between us humans and better systems that deliver the services that we need. Okay, and I think that these challenges are transnational, right? Global, right? They are not specifically US challenges or European challenges. Maybe there are aspects of them that are specific to certain contexts, but I think that we're talking about global problems here. There is a need, there's a convergence of needs here that creates an opportunity for collaboration. We can co-invest. There are schemes to co-invest across the 2 continents in bilateral research projects. We can share experimental test beds. We can share open standards. In all the areas that I talked about, and in more areas probably, we can develop these things together. So I think that this is an opportunity we can capitalize on, both by applying, of course, for funding to the existing mechanisms, but also by influencing our funders to pursue these collaborations more actively and showcase the benefit of these collaborations. Okay, so I'm going to thank our funders for this effort specifically. It's National Science Foundation Ireland, the Northern Ireland Department for the Economy, of course, the European Commission that funds the Discover US project and the collaboration with Dimitris. Some more people, in addition to Dimitris, of course, here, the SWEET team, Deepu, Hans, Bo, Xianchen, Kazi, Farhana, Ajay, Syed, Yike, and Jinyi. They are all the principal investigators and students. And of course, the Parva GPU team where we originally worked together on the GPU partitioning project, Myungkyu, Sihun, Minki, Jihyuk, Gapju, Injel, and Jolho. And with that, thank you very much for listening to this webinar, and I'm happy to answer any questions that you may have.
Thank you, Dimitris. I don't see any question in the Q&A channel. Please, if you have any question, don't hesitate to throw it there. We have very little time, but let me maybe ask one at least.
Yeah.
When you were presenting the HiPEAC, I don't know how you pronounce it, the HiPEAC. You were talking about having a budget. I understand that if you have a larger number of tokens, then the quality can be better, no?
Yes.
So
yes.
how you decide the budget?
Yes. Okay. So only empirically at this moment, right? So there is no, we don't have a good automated algorithmic approach to decide the budget. So we try to empirically select it by considering the device constraints, right, and the quality, the potential quality impact that we have here. So it's a good question, Rosa. So we don't have a good way to do that other than basically try to formalize a little bit a combination of device constraints and quality, overall quality. We're working on this a little bit. So we have what we call a cost model that considers basically these two aspects, right, of the budget and the potential cost to the user of spending these tokens. And we try to do some optimization against that, but we haven't yet published anything there.
Okay.
So it's an empirical decision. Yeah.
I see. We have a question from our coordinator, Conde Boucher.
Yes.
So he's asking if SWEET is a collaboration between NSF and Ireland.
Yes.
And he's asking if there are similar schemes between the US and the European Commission beyond Discover Us.
Right. Yes. Yes. So there is no scheme with the entire European Commission, right? Okay. So there's an NSF UK. I'm not aware of a scheme that involves the Commission as a body. And I think that's, that's something that is missing a lot. I think there are schemes with Japan, there are schemes with Brazil, there are schemes with many other countries. And I know that they have been very successful in the sense that NSF has retained them and run them for many years and funded them quite well. One thing I want to mention to Kuhn here is that these schemes compete for NSF funding effectively with other NSF priorities, right? So the fact that these schemes continue is very encouraging, right? So the fact that NSF still allocates money for these schemes for international collaborations is very, very encouraging. But there is nothing there that has the European Commission as an overall kind of like partner. Okay, there is one exception, and this is the ERC, right? So NSF has a specific scheme that involves US investigators and ERC holders, and they can establish an international center of sorts, as I understand, together and work on common problems. So that's the only exception where you have a European Commission-led, I guess, research scheme and NSF, but it's not the European Commission, Horizon, for example, programs.
But I understood that this scheme with ERCs was for visits only.
Yes. Yes.
Not to fund research.
Not to fund projects.
Visits.
Yeah, not to fund a project.
Yeah, because we were told by our NSF officer unfortunately is not there now.
Yeah.
Bueno. Okay, thank you very much. I think we will need to conclude. So thank you again, everybody, for attending, and especially Dimitris for his talk.
Thank you.
Thank you.
Thank you.
Good to see you. Bye-bye.